Earth's atmosphere is like a giant blanket, enveloping our planet and providing essential protection. It shields us from the harsh environment of space, including harmful solar radiation and meteoroids. This protective blanket is made up of several distinct layers, each with its own unique characteristics and functions. These layers are known as the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. The troposphere is the layer closest to Earth's surface. This is where we live and where all our weather occurs, from gentle breezes to powerful storms. Above the troposphere lies the stratosphere. The stratosphere is home to the ozone layer, which absorbs and scatters the sun's harmful ultraviolet radiation, protecting life on Earth. Next, we have the mesosphere. The mesosphere is the middle layer of the atmosphere, and it's where meteors burn up upon entering, creating shooting stars. Beyond the mesosphere, we enter the thermosphere. The exosphere is the outermost layer, where the atmosphere gradually fades into the vacuum of space. The thermosphere is a crucial layer, despite its thin air. It's where many fascinating phenomena occur, such as the auroras, and it's also the region where the International Space Station orbits. Let's delve deeper into this high-altitude frontier and uncover the mysteries and wonders of Earth's atmospheric layers. The thermosphere is above the mesosphere. It starts about 53 miles or 85 kilometers above Earth. It extends up to 372 miles or 600 kilometers high. This makes it very tall. This layer is not dense. There are few air molecules. Even though it's high up, it's not empty. It's full of activity. The thermosphere is where the auroras happen. These are the northern and southern lights. Satellites and the International Space Station orbit in this layer. The thermosphere merges with the exosphere. The exosphere is the final boundary before outer space. Ultraviolet or UV radiation comes from the sun. It hits the thermosphere first. UV radiation has a lot of energy. It breaks molecules apart, and this process is called photoionization. When molecules break apart, they become ions. Ions are charged particles. They have extra or missing electrons. Photoionization creates many ions in the thermosphere. This is important for communication. Ions can reflect radio waves, which helps radio signals travel long distances. Photoionization also causes photodissociation, breaking molecules into smaller pieces. Both processes are vital in the thermosphere. The ionosphere is a part of the thermosphere. This region of the atmosphere is located approximately 80 to 600 kilometers above the Earth's surface. It plays a crucial role in atmospheric science and space weather. It's where many ions are found. These ions are created when solar radiation ionizes the atmospheric gases, stripping electrons from atoms and creating a sea of charged particles. The ionosphere is divided into layers. Each layer has distinct characteristics and plays a different role in the behavior of radio waves and other electromagnetic phenomena. These layers are D, E, and F. They are named based on their altitude and the density of ions present in each layer. The D layer is the lowest, and it absorbs low-frequency radio waves. This absorption can cause signal loss for certain types of communication, especially during the daytime when the D layer is most active. The E layer is in the middle, and it reflects medium-frequency waves. This reflection is essential for medium-range radio communication, allowing signals to travel beyond the horizon. The F layer is the highest, and it reflects high-frequency waves. This layer is particularly important for long-distance communication, as it can reflect signals over vast distances, even across continents. The ionosphere is crucial for communication. Without it, many forms of radio communication, including amateur radio, aviation communication, and even some forms of satellite communication, would be impossible. It helps radio signals bounce back to Earth, which is vital for long-distance communication. This bouncing effect, known as skywave propagation, allows signals to travel far beyond the line of sight. The ionosphere changes with the sun. Solar activity, such as solar flares and sunspots, can significantly alter the density and composition of the ionosphere. During the day it has more ions, and at night there are fewer ions. This affects radio signals. Daytime ionization increases the density of the D layer, causing more absorption of low-frequency signals, while nighttime conditions enhance the F layer, improving long-distance communication. Section 5. Solar ultraviolet radiation and geomagnetic activity. The sun's UV radiation is strong. It affects the thermosphere greatly. Solar activity changes over time. This causes the thermosphere to change too. Solar flares and geomagnetic storms can increase ionization. This makes the thermosphere more active. It gets hotter and denser. This can disrupt communication. Geomagnetic activity also affects the auroras. Strong solar winds create bright auroras. These can be seen closer to the equator during storms. The thermosphere acts as a shield. It protects Earth from harmful solar radiation, but it also reacts to solar changes. Section 6. Temperature and variability in the thermosphere. The thermosphere is one of the outermost layers of Earth's atmosphere, sitting above the mesosphere and below the exosphere. The thermosphere is very hot, with temperatures soaring to extreme levels. Temperatures can reach up to 4,500 degrees Fahrenheit or 2,500 degrees Celsius. This intense heat is due to the absorption of high-energy ultraviolet and X-ray radiation from the sun. But despite these high temperatures, it doesn't feel hot to us. There are too few molecules to transfer heat effectively. The density of particles is so low that they rarely collide, making heat transfer negligible. Temperature in the thermosphere varies significantly with solar activity. More solar activity, such as solar flares and sunspots, means higher temperatures in this atmospheric layer. Conversely, less solar activity results in lower temperatures. This variability makes the thermosphere a very dynamic and ever-changing environment. The density of the thermosphere also changes in response to temperature fluctuations. Higher temperatures cause the thermosphere to expand, increasing its volume. Lower temperatures make it contract, reducing its volume. These changes in density and volume can significantly affect satellite orbits. Scientists study these changes meticulously. Understanding them helps predict satellite behavior and ensures the safety and accuracy of satellite operations. This research is crucial for maintaining communication, navigation, and weather forecasting systems that rely on satellites. Section 7. The role of the thermosphere in communication. The thermosphere plays a key role in communication. Its ions reflect radio waves. This allows signals to travel far. During the day, the ionosphere is denser. This helps shortwave radio. At night, it's less dense. This changes the way signals travel. Geomagnetic storms can disrupt communication. They change the ion density. This can cause signal loss. Predicting these changes is important. Satellites also use the thermosphere. They rely on it for stable orbits. Understanding the thermosphere helps improve satellite communication. Section 8. Human activities and the thermosphere. Humans impact the thermosphere. Rocket launches release gases. These can change the ion composition. Satellites and space debris are present here. Debris can collide with satellites. This is a concern for space missions. Scientists monitor the thermosphere. They track debris and study its effects. This helps protect satellites and astronauts. Human activities in space are increasing. Understanding the thermosphere is more important than ever. Section 9. Scientific research in the thermosphere. Scientists study the thermosphere closely. They use satellites and ground-based instruments. This helps them understand its behavior. Research focuses on many areas. These include temperature changes, ion composition, and solar effects. Data from satellites like the timed mission is valuable. Ground-based observatories also help. They measure radio wave reflections. This provides information on ion densities. Collaborative research is key. Scientists from different countries work together. This expands our knowledge of the thermosphere. Section 10. The future of thermospheric study. The study of the thermosphere is ongoing. New missions are planned. These will provide more data. Technology is improving. This allows for better instruments. Future studies will be more accurate. International cooperation is vital. Sharing data improves understanding. Global networks of observatories are being developed. The future of thermospheric study is bright. Continued research will reveal more about this fascinating layer. Section 11. Conclusion: significance of the thermosphere. The thermosphere is a vital part of Earth's atmosphere. It interacts with solar radiation. This creates ions and affects communication. It acts as a shield, protecting us from solar radiation. It also hosts the auroras, adding beauty to our night sky. Understanding the thermosphere is crucial. It helps improve communication and protect satellites. Continued research is essential. The thermosphere is truly Earth's high-altitude frontier. Its study reveals much about our planet and beyond.